So far in mechanics, all the forces we've been working with have generally been either horizontal or vertical. In this section of the notes, we're going to learn how to deal with forces that are not horizontal or vertical. This process is called resolving forces, and the process of representing a force in terms of two components is referred to as resolving the force into its components, or sometimes called into its resolved parts. So generally we take a single force and we're going to resolve it into two components, one which is horizontal and one which is vertical. So the most usual way of resolving a force is into components along two perpendicular lines, such as the x and y axes. In a lot of cases it will be this, it'll be horizontal and vertical. Later you'll see some examples where we're working with a slope or an inclined plane, and then in that case we then go parallel to the plane and perpendicular to the plane, but that's coming up later. So if we take a look at this diagram, we've got a force of magnitude capital F, and it's going to become two perpendicular forces, the two component parts that make up the original force. F is at an angle of theta to the horizontal. So if we do a little bit of right-angled trigonometry here, let's take this triangle first. The vertical is the same length as F subscript y. That's the opposite to the angle. And we know from right-angled trigonometry that sine of an angle is opposite over hypotenuse. So sine theta is opposite, which is Fy, over the hypotenuse, which is F. By rearranging this, we get F subscript y is F sine theta. F subscript y represents the component of the original force F in the y direction. So F subscript y can be worked out by multiplying the original force by sine theta. Now theta here is the angle between the force and the horizontal. Things would be different if theta was this angle up here. So don't jump to the conclusion that the vertical force is always sine theta. It isn't. It depends on which angle is theta. Similarly, we can do adjacent over hypotenuse, which is cos. So cos theta, which is the adjacent, fx, over the hypotenuse, which is f. So rearranging that, we get f multiplied by cos theta gives us fx. And that gives us our two components from the original force. Now the way I've always remembered this is just focusing on this one. So there's not really two things to remember here. If you remember one of them, then you automatically remember the other. And also it's not all about remembering, is it? We can use right angle trigonometry to work it out. Anyway, the one I've just put a rectangle around, F subscript x, which is F multiplied by cos of theta. I've always just remembered that it's the cosine of the angle between the force and the direction that you're trying to get it into, or the direction of the component you're interested in. So I'll say that again. It's the cosine of the angle that you need to turn the force through to point in the direction that you're working. Let me show you what I mean by looking at the other one, the vertical component. So this angle here would be 90 minus theta, because together these two angles make a right angle. So if I go back to what I said earlier, the component is always the original force multiplied by the cosine of the angle between the force and the direction of the component you're currently trying to get. So this would be F cos of 90 minus theta. And I hope you remember that cos of 90 minus theta, it will always be the same as sine theta. I'll write it up here. That is true for any angle theta. It's also true the other way around. Cos theta is the same as sine of 90 minus theta. That's true for all values of theta. So these two expressions are the same. You'll get the hang of this as we go through examples. So first example, find the x and y components of the following forces. Hence, write each force in the form pi plus qj, where I and j are the unit vectors as usual in the x and y directions respectively. So the first one, on part A, we have a force of 3 newtons acting at 37 degrees to the horizontal. I'm just going to use the same notation as earlier, fx and fy. So if you want to, you could draw a right angle triangle and then think about opposite over hypotenuse and adjacent over hypotenuse to work out the forces, the two components. I'm just going to use that phrase that I said a moment ago. The component is always the force multiplied by the cosine of the angle between the force and the direction of the component you're currently trying to get. So because I'm currently focusing on the horizontal component, that's going to be cos of 37 degrees. So that's fx. There's no particular reason that I've put the angle in brackets. It just happened. The vertical one, I'm going to use the same process. Now you might like to do it the way I'm doing it, or you might just do it like it was on the top of the page where we used right angle trigonometry to work it out. But here's how I like to do it. Cos of the angle that we need to turn through. So this is 53 degrees. So that would be correct, 3 cos 53 degrees, which is the same as 3 sine 37 degrees. So either of those two answers here would be correct. They're both correct, in other words. Now hence write this in the form pi plus qj, where I and j are unit vectors in the x and y directions respectively. So in this case the force is 3 cos 37 degrees I plus, I can go with either of the versions here. I'm going to go with sine. So there we go, that's the force represented in vector notation. So have a go at the next two now. Pause the video if you feel that you can. Otherwise, just listen to my explanation of doing these. So part B, force 5 newtons at 140 degrees to the horizontal axis. By the way, just to put a bit more detail on here, I and j unit vectors in the x and y directions respectively. That's the positive x and y directions. When a question says in the x and y directions, it means in the positive x and y directions. So for part B, I'm going to work out a couple of angles. First of all, this one, that must be 40 degrees, because angles on a straight line add up to 180, and this one here must be 50 degrees. Now there are many ways we can do part B. Let's do the horizontal component first in the positive x direction. So there's many ways we can do this. I'll write down all the different versions, so any of these would be correct. First up, 5 cos of 140 degrees. We're turning it through 140 degrees, and it's cos of the angle you need to turn it through. So there's one way of doing it. Or we could turn it through these 40 degrees here, but then it would be pointing in the negative x direction. So we could also have negative 5 cos 40. That would also be correct. So just to reiterate, both of these are correct. They're both the same value. For Fy, you could write down 5 and then cos of the angle you need to turn it through to point in the y direction. So 5 cos 50 degrees, that would be correct. If you had 5 sine 40, that is also correct, because cos 50 and sine 40 are the same. So we can now write the force in vector notation. And there we go, minus 5 cos 40 I plus 5 sine 40 j. Now I've got part C. If you feel you can, pause the video and have a go. So the horizontal component, 7 cos 50 degrees. For the vertical component, we can either turn it through 140 degrees, so it's 7 cos of 140 degrees. That's one correct version. Alternatively, this angle between the 7 Newton force and the downward vertical is 40 degrees, so we could turn it through that, but because it would then point down, I need to put a minus. So another version is minus 7 cos 40. That is also correct. Another correct version, minus 7 sine 50. All three of those versions would be correct. So now we can write it in vector form. And it doesn't matter which version you go for, as long as it's correct. There's the one I've gone for. So that completes an introduction to resolving forces and example 1.2.1.